Hello, and welcome to the last talk of Wednesday here at Black Hat. You're in the Jasmine room today, and you're here to see, hopefully, the Node.js Highway by Amit Ashbel and Mati Simon. There are a couple of quick announcements. There's a reception tonight, right now in the business hall, but you're here, which is probably a much better choice. Then at 6:30, the Pony Awards happen in the Mandalay BCD room. I know earlier a couple of times we said 6 o'clock. It's actually 6:30. And if you have cell phones, make sure that they're on a vibrate mode or some kind of a silent mode so you don't have crazy ringtones interrupting the talk. That's it. Thank you and enjoy.
Good evening, everyone. As we were presented, I am Mati Siman, and together with me is Amit Ashbel. During the last year, we did some research regarding Node.js to add Node.js support to our product. We both work for Checkmarks, and we found some interesting stuff regarding Node.js, and we felt that many people don't know these aspects with Node.js, and we thought it would be nice to share these insights or these findings with the community. So in the next 30 minutes or so, we will show you some interesting stuff. Actually, there were some additional issues that we wanted to show, but because this is a fairly short presentation, we won't show everything. Feel free to join us at our booth to see some additional issues. Amit?
Thank you. Hi, everyone. So, as presented twice already, my name is Amit, and we'll jump right to it because we are very limited in time. In terms of the agenda, we'll quickly cover the Node.js architecture. And after the architecture, we'll go through some of the vulnerabilities or some of the wrong programming techniques that Mati mentioned a second ago. They'll include items like denial of service, some weak crypto, SQL injection with no SQL, and regex denial of service. So let's go ahead and talk about the architecture. So Node.js, as some of you may know, is a single-threaded, event-driven application framework. The idea is that you have the event loop in the center, which you can see, and the event queue, which constantly delivers content to the event loop to handle. Now, the event loop won't handle most of the content itself. It will pass it on to the event to the I/O section in the process, which will then go ahead and perform the actions and pass it back. Any callback that's left over will pass back to the event queue, so that in this case what happens actually is the event loop is constantly available to perform tasks in a quick manner. If we look at it in a more human-readable way, you have the single thread at the cash register at the fast food restaurant, and you have the event handler. Now the queue, which we can't see here, is constantly handing over actions for the single thread, and that single thread is passing these actions on to the events handler. Okay? That way, the single thread, the guy at the register, is constantly available to take more and more orders, and there's no need for multiple actions because he has these handlers doing the work for him. Now, what's good and bad about that? There's a lot of advantages for Node.js. The fact that it's very quick with I/O. It's good with DB queries. We'll see that in a second. And it's good for applications that have high user interaction, so web applications mainly. However, when we move over to CPU-intensive applications, it's less of a recommended method to use, because in that case, you'd actually be making the event loop working too hard, and it won't be available to go on and perform other actions with the event handlers. So, denial of service. What we see on the screen here is a few lines of code that what it does actually is sum up a number between 1 and p, where p can be any number that you choose. And we want to see why this is actually related to denial of service. And this is actually our first demo. So you have two screens here. Each one of them is going to run that script that we just saw. So in this case, you have the number 5, p equals 5. So it's going to sum 1 through 5. Okay? And if I click that...
They don't see it on their screen.
Yes, they do. Do you see it?
No, it's cut. The left-hand side is cut.
Ah, okay, let me put it on full screen. Better?
No.
Still cut.
Go just smaller.
Okay. So, now this is actually running through an Node.js framework or Node.js code. Once I click the 5, it automatically does the action, calculates 1 through 5, and it gets the number 15. Very simple. Then I go to a higher number. So in this case, it's 1 with a lot of zeros, and I'll add in another 0 just to make sure. And it's going to require more CPU activity, and therefore it's going to take more time. At the same time, I'm going to run the 5 again, and we'll see if I get it fast enough that it's going to wait until this one completes. So you see that the one with the large number is still running, and the 5, which previously took a second to complete, is not completing yet until the other one completes. So let's give it a second, and you'll see that it happens one after the other in a second, once it happens.
I think you added an extra 0.
I think I added too many zeros.
No.
Okay, it's running in the background. The idea here is that it's currently not being able to process anything else. If we look at the task manager, we'll see that the thread is currently using 25% of the CPU, which is a full core out of the quad cores that this laptop runs. So once it finishes, and we probably won't have a chance to see it finishing, the other one will immediately be processed and completed within a second. So that's a problem. You can actually, and I think I've denied myself of service at the moment. But the idea is that if you run a high CPU intensive application, Node.js is not the right way to go. And with that, I'll pass it over to Mati. Thank you.
Thanks, Amit, for breaking the laptop just before my part of the presentation. It's a great idea. So we'll get back to denial of service later on when we describe the regular expression denial of service, but it was important to describe the architecture behind Node.js. Allocate all CPU. The next part will describe a little bit about weak cryptography. So as part of the research, we went through some open source projects, and one piece of code that actually caught our eyes was this code in here. It was part of a system that authenticates user, and something that competes with OAuth, allows you to integrate multiple services into same authentication mechanism. Obviously, we hid some of the information, but can anyone tell us what's wrong with that code in here? The MD5 is one of the problems, yeah. Yeah, math random, exactly. So basically the idea is when a new user registers, the system generates a new random or pseudo-random number, and then generates the MD5 of that number and returns it back as the user's password. So there are two issues in here. The first one is that math random is not really random. That's pseudo-random, obviously, and it's fairly weak, and we'll see that. The other part is that MD5, although it is a strong or fairly strong hashing algorithm, it can be reversed fairly easily. So we'll see how we actually break that specific code. Okay, so let's talk a little bit how the pseudo-random number generator works for V8. Okay, V8 is the engine that runs behind Chrome and also behind Node.js. That's the very same engine. So basically we start with the seed number, okay? The seed is usually based on the timer when the system started, so that's usually based on the time. And then from the seed, we get the state 0, which is a private value, a very secret value, internal value to the random generator algorithm. And from state 0, we actually derive two numbers. Part of it is the random that is presented to the user or is given back to the developer. And then we also derive the next state, in that case, state 1 value. So we have the seed, we have state 0, and then we roll it to state 1, state 2, state 3, and each one of them we can derive its random number. Now, this is a one-way algorithm. So given random 0, we can't compute back state 0. Why is that? What would happen if we were able to compute back state 0 from random 0? Okay, so once a hacker has access to state 0, he can compute all subsequent states and all future random numbers. Okay, that's why these states are very secret. This was discovered by Amit Klein a few years ago. Google, which runs V8, actually modifies the algorithm every so often. There are some magic numbers behind the scenes. I won't present it right now, but they change it in every few versions. So basically, if we take a look back at the code, we need to do three things. First of all, V8, based on Amit Klein's research, given 3 random new passwords, if we know what were the random values, we can compute all future ones. So first, we need to reverse the MD5 of 3 passwords. Given the MD5, we need to compute back what was the random number as the root. And then given 3 such numbers, we can compute all subsequent values and compute all next passwords. Okay, there are many cases where this can be helpful. For example, let's say that we have a system and a user clicks on forgot password and the system generates a new password for him. So as a hacker, I can do 3 times I forgot my password. I will get 3 valid new passwords, and then I can hit forgot password on behalf of a different user just by providing the other user's mail. And even without having access to the mail, we can tell what is the newly random number. Okay, in our demo, we will do something a bit different. So, given 3 consecutive random values, we can compute state 0 and state 1. Google knows about that, but it is considered as low risk. The reason it is considered low risk is because in Chrome and other browsers, each tab has its own state. So state 0 in one of the tabs is different than state 1 or state 0 in other tabs. So even if a specific website is able to know what's its own state 0, it means nothing for other tabs in the same browser. That being said, while using V8 as part of Node.js, it means that all users that are using the same Node.js server actually share the very same state 0. So one user can compute its own state 0, and it will hold true also for other users. Let's see how it works. So our user will register as fake user 1, okay? And he gets back, as a result, the fake user 1 password. And then he will register as fake user 2, and will get fake user 2 password. Register as fake user 3, and get fake user 3 password. Okay, as a reminder, you can see here the code, okay? Then we will send all 3 passwords, which are MD5 hashed, to our rainbow table, okay? We've created the rainbow table specifically for these random numbers, okay? So we will send it to a cloud service, which computes back the MD5. What we'll get back as a result are the clean random numbers. Okay, so we get back the clear random of all 3 passwords. And then we will send this to some magic, once again, on the cloud that computes the state 0 out of 3 consecutive numbers. We'll compute the 4th number. Then we create the hash code of it, and we'll know what would be the password of the 4th user. Make sense? Perfect. So let's see how it works. Okay, now I know that the screens are a bit cut because of resolution, so let's try to do the best out of that. Yeah. Okay. I guess you're laughing because of that, yeah? Fair enough. So let's register as the first user, okay? User 1 and email whatever you want. Let's register. Oh, internet connectivity. No good. Just a second. Amit, can I have your laptop, please?
You want to ruin mine now?
Yeah, I owe you one. Okay, so good that we had a backup laptop. Okay, so let's user one, let's register. Let me just zoom out a bit. And we got the first user's password. That's the MD5 of the password. Now we will run it against a rainbow table on the cloud. Okay, that's a fairly large rainbow table. It's about 200 gigabyte large. Okay, and what we got is the plain value that actually the reverse of this MD5. Let's put it in here. Okay, that's the first PRNG. Let's register as user 2. And we got the second password. Okay, back to here. Let's reverse it. Okay, and now let's take the third password. And reverse it. Okay, so far we have the 3 clean values that were used to compute the password, and now I will run the algorithm that actually computes the next so-called random number. So let's run it. While this is running, oh, it was quick. It's good. No, I hope it was okay. Okay, so the system tells us that the next password that should be random is the one that begins with E2 and ends with FCC. Okay, so that's what the system believes will be the next password. So now let's register as a real user. And fair enough, E2 and FCC. Okay. So the reason that we had to create a rainbow table is that all publicly available rainbow tables are ones that are used to decrypt passwords. So they're usually limited to 8 to 10 alphanumeric characters. And okay, 8 to 10 numeric characters. Now the actual number that is generated by random is much longer. It's usually 16 digits long. In that case, no publicly available random table. We couldn't find any rainbow table, so we had to create our own. Getting back to the presentation, actually, I'll switch back laptops for a second. A little bit about SQL injection, NoSQL, MongoDB. So MongoDB, for those of you who don't know it so well, it's a document-oriented database. So there are no records, but rather documents, and then there are no tables, but there are collections. Okay. So for example, at the very same collection table called products, we can add one record, one document, where the value item is card and the value of quantity is 15. And then in the very same collection, have another document with name elephant and size 1700. In order to find values in these collection, we can use product find, which finds everything, or we can issue filtering using JSON format. For example, we can limit to all the ones that their quantity is 15, or we can use sub-expression, and that's crucial. We can limit to quantity that is greater than 25. Okay, so everything is JSON-based. The filtering is JSON-based, and the parameter for the filtering is also JSON-based. Now, we know JS, there is a one-to-one correlation between JSON structure and objects. So every object is automatically translated into JSON and back and forth. So we could have done the same by using var object, obj.quantity equals to 15 or 25, and then do db products find obj. Okay, so it's important to note for this slide that filtering MongoDB requests or queries is based on JSON, and you can do it either by sending the JSON itself or an object with the relevant values. Let's see how it gets really interesting. So that's obviously a SQL injection. Most of you, or hopefully all of you, know that. So that's fairly easy. In MongoDB, since there is no SQL, so there is no SQL injection, as Amit said. So let's say that we create an object called name, that its value is taken directly from the query string, and then an object called password directly taken from the password, and then we do db users find, and then we find places where username equals to is name, and the password equals to password, and then we do some if exists. Do you think it's a good solution? Obviously the answer is no, otherwise we won't be here, but why is it? Okay, so the fun part is that although in most cases name is actually a string, we saw earlier that we can actually use a sub-JSON expression. So if the name was actually a more complex object with data members, it would have been automatically expanded in here, and we could have used some other operators rather than just equal. And let's see how it is done. For example, we can use db find username is greater than a, and then use password greater than a. So without knowing any valid username and password, assuming that the username is greater than a, and then the password is greater than a, we would be able to log into the system. Okay? So as a reference, you can see the full blog at WebSecurify's site. So let's see how it works. So let's start with some. That's weird. Let me disconnect. Otherwise, I'll use Amit laptops again. It worked. Okay. So let me zoom in a bit. Okay, so if we try to log in as admin, I think we're welcome back admin, that's fine. If we make a mistake, A, B, C, D, E, F, okay, doesn't work. In order to make it, well, simpler for this presentation, instead of post, we will be using the get, but it's actually the same. Okay, so we can use admin in here, and if we make a mistake, that's bad. And as promised, we can use $GT greater than A, and then $GT in here. And it automatically creates an Node.js complex object and then serialize it when it's sent to the MongoDB. And welcome back admin. Okay, so without you using any valid username and password, we're able to log in. And I actually can enumerate all users, so I can use here B, and I see a different user. Okay, so we can just go through the system and do that. Okay? Thank you. Thanks. One way to fix this issue is to use, and that's what we usually see in projects, is to use the following. We do DB users find get the user object that has that specific username, and then compare the password stored in the database with the password provided by the user. Okay, so we don't let the MongoDB to validate both username and password. We just retrieve the username from the database, and then we compare the retrieved password with whatever the user typed in. Make sense? Okay. This is a good solution. No, not so much. Why is that? So we've used the $GT to compare if a value is greater than. There are about 30 different operators that can be used. One of the operators, one that I personally like very much, is the regex operator. Okay? It allows you to find entities in the database that match a specific regular expression. Now, back to Amit's part, we know that Node.js is highly sensitive to CPU-intensive tasks. Regular expression is highly, 5 minutes left? Perfect. Or not so perfect, but okay. So knowing that Node.js is very sensitive, and regular expression takes a lot of CPU, and we can use both to do some kind of really interesting denial of service, like that. Just a second, let me copy it from my slide deck. It's okay. I hope it's okay. Let's see it. Okay. So let me paste that into here. And let me open the CPU. Okay. Now I hit enter. And you can see that MongoDB in here takes 25% CPU. I have 4 cores. So a single request consumes a full core to work on. And it takes a few seconds. Obviously, the more A's I've been adding, the longer it would take. Sending 4 requests would take 100% of my laptop. And obviously, we can very easily consume all CPU cycles from the server just by sending 4 or 8 requests. So we can do it constantly. So it will actually block completely the MongoDB that works behind the scenes. Okay. Actually running out of time. So if there are any questions, there are 2 minutes left. So if there are any questions, that's a great time right now. Okay. So there are some additional topics that I wanted to cover. Feel free to stop by our booth tomorrow. Either Amit or myself will be there, and we'd be happy to help you. Thank you very much.